Hello everybody, this is group 31 of Chem 262 and today we're going to be discussing PFAs, otherwise known as forever chemicals.
So what are PFAs? They are what is known as per- and polyfluoroalkyl substances, and they do not occur in nature and are completely man-made. PFAs include groups like PFOAs, PFOs, and Gen X. PFOA, or perfluorooctanoic acid, and PFOS, or perfluorooctane sulfonate, are fully fluorinated chemicals that are part of a bigger group known as perfluorinated alkyl acids. These two PFAs are the ones that have been studied the most, and rightly so, since they have been the ones that were most heavily produced since the 1940s. Gen X is actually a type of technology that is used to create fluoropolymers without using perfluorooctanoic acid. However, in its place, the technology still uses other types of chemicals that are released into the environment, like HFPO, dimer acid, and their ammonium salts. There are also lesser produced PFAs like perfluorohexane sulfonate and perfluorobutane sulfonic acid. And these types of PFAs are not used as much and they are not as researched as PFOA and PFOs.
The first PFAs were invented in the 1930s and were the main ingredients in non-stick and waterproof coatings. Development of these chemicals increased in the late 1960s after a deadly fire aboard a U.S. Navy aircraft carrier, the USS Forrestal, in 1967. The fire resulted from the accidental launch of a rocket into armed planes and loaded fuel tanks. This blaze nearly destroyed the ship and killed more than 130 people. Soon after the tragic incident, manufacturers and scientists developed PFAs containing aqueous film-forming foam, or AFFF, a foam mixture that rapidly extinguishes fire. The PFAs allow the mixture to spread, making it highly effective against petroleum fires and other flammable liquid fires when mixed with water. PFAs containing AFFF was subsequently installed on military and civilian ships, airplanes, and airports. Today, more than 3,000 synthetic chemicals are classified as PFAs. They have a wide-ranging application, such as in grease-resistant microwave popcorn bags, carpets that resist stains, and pipes and wires that resist corrosion.
So where are PFAs found? PFAs exhibit both hydrophobic and oleophobic properties. That means that there is a plethora of applications for PFAs. They can be found in things like water-resistant coatings and polishes. They can also be found in a lot of cookware because they use it to make them non-stick due to the oleophobic properties. Looking down here, we can see that PFAs can also be found in some certain types of plastics, but not only that, they can be found in drinking water. And that's where the problem is. Since PFAs are getting into the water supplies, PFAs are also being detected in people, and it is here where we see some problems.
There is evidence that exposures to PFAs can lead to adverse health outcomes in humans. If humans or animals ingest PFAs by eating or drinking food or water that contains PFAs, the PFAs are absorbed and can accumulate in the body. PFAs stay in the human body for long periods of time, and as a result, as people get exposed to PFAs from different sources over time, the level of PFAs in their bodies may increase to the point where they suffer from adverse health effects. The most consistent findings from human epidemiology studies are increased cholesterol levels among exposed populations, with more limited findings related to infant birth weights, effects on the immune system, cancer for PFOA, and thyroid hormone disruptions for PFOS.
So now let's talk about the very interesting chemistry behind PFAs. So PFAs are basically comparatively long carbon-fluorine structures with an acidic head to them. If it's PFOA, usually they have a carboxylic acid head, and if it's PFOS, they have a sulfonic acid head. If you look at them, they're actually in some ways similar to soaps because they have a head and tail. Unlike soaps, they have an acidic head, which is quite polar, and a fluorinated tail. Coming to the properties of PFAs, this is the stuff that really makes PFAs special and harmful. So as we talked about in the last slide, PFAs are long carbon-fluorine chains, and the carbon-fluorine bond is very, very stable. This is because of fluorine's high electronegativity, it just doesn't break. And so for this reason, they're hard to break down within the body, and they're constantly persistent in the air, in nature, and they're harmful for the environment as well. And this is why they are in fact called forever chemicals. Another very interesting property of PFAs, and the reason why it's used so much, is because PFAs are lipophobic in nature. This reduces the surface tension of water, but more importantly, what it does is it basically doesn't allow it's lipophobic, which means that it hates fat. Lipophobic comes from the word lipids, and lipids basically means fat. So it hates fat, and for that reason it's used a lot in frying pans and cooking utensils, because the oil doesn't stick onto the pan for this reason, and this is why it's so widely used.
Okay, now we will finally discuss the actual reaction involved in forming these PFAs, which is a synthesis reaction, of course. In this instance, we will be discussing the synthesis to form PFOA, although this does work for PFOS. Now, there are two types of synthesis routes used for PFAs: electrochemical fluorination, otherwise known as ECF, and telomerization. Now, telomerization here is far more pertinent than the electrochemical fluorination for Chem 262, so will be discussed first. Now, in this reaction, there is a radical polymerization that occurs. In this radical polymerization, a telogen is reacted with an unsaturated taxogen molecule. In this instance, our taxogen molecule is consistent throughout each individual addition reaction, and it is the tetrafluoroethylene. Okay, now this reaction is a very linear reaction, wherein the same tetrafluoroethylene is continually added to each product or that is formed in this case, and it is added along the double bond, the alkene that is present in the tetrafluoroethylene. Okay, and it's just essentially a polymerization, continually adding CF2 groups to the product, and after that is completed, okay, it is finally oxidized with our SO3 to form a PFOA group.
Now let's go over ECF just for a little bit. ECF is a very basic addition reaction where you replace the hydrogen in your hydrocarbon chain with fluorine atoms. This on the outside looks like a very simple synthesis, but it's an electrochemical synthesis which is much more complicated, and which I'm not going to get into at this point. Along with this, actually telomerization is less commonly used as compared to ECF, and ECF, just like telomerization, also produces PFA derivatives. These derivatives, just like telomerization, are removed through simple distillation. I also had a really fun fact about ECF. It's that actually ECF was devised and created in the 1930s, but it was not in fact published until after World War II, because ECF is used for uranium fluorination. Now, this was just an interesting fact that I found very cool, and I shared it.
Due to the chemical's persistence in the environment, drinking water can become contaminated with long-chain PFAs that includes PFOA and PFOS. This is one of the primary concerns of human and animal exposure to the substances, according to the EPA. Many people are trying to do something to fix this pollution problem. For example, a water treatment group in North Carolina is building a new facility that will contain large filters of granular activated carbon to suck PFAs out of contaminated drinking water. Other researchers are trying to find ways to completely destroy the PFAs once they have been filtered out of the water in order to limit long-term waste. In early 2019, the EPA announced its Per and Polyfluoroalkyl Substances Action Plan. This includes both short and long-term actions to help officials better understand the chemicals and clean up of PFOA and PFOS chemicals from contaminated water sources. The plan that outlines how the EPA works to work with other agencies and manufacturers to research and monitor the development of new and existing PFAs. as well as how the agency intends to provide detailed information and risk communications to the public. Researchers and manufacturers are also working to incorporate shorter-chain PFAs in place of the long-chain chemicals to see if the chemicals can achieve the same useful properties. Short-term PFAs may be less harmful and are less likely to accumulate in humans and animals, according to the EPA.